If you're anything like me, you really love those moments where a completely ordinary, simple concept just suddenly flips upside down.
Oh, yeah, that sudden paradigm shift.
Right. You know that feeling when you learn a single fact that just completely rewires how you view the room you're sitting in right now. Well, today, we are taking something you have literally been bathing in since the very first day you opened your eyes.
Light.
Light. And we're going to look at it in a way that is deeply, wonderfully strange. Welcome to this custom-tailored deep dive. Our mission today is to give you the shortcut to being truly well-informed about the physical reality of our universe.
And we're doing it without drowning you in complex math or information overload.
Exactly. We're exploring a remarkable text today, the Autobiography of Light by Lucia Verdandi. Specifically, we're looking at the expanded edition by Max and Claude.
It's a fantastic source.
It really is. And our goal is singular here. We are going right down to the fundamental level to explore the literal physical reality of what it is to be a photon. We aren't talking about light as some, abstract metaphor for knowledge or goodness today.
No, not at all.
We are looking rigorously at the fastest, loneliest, and most bizarre messenger in the cosmos. To help guide us through this mind-bending territory, I'm joined by our resident expert, and I see your backdrop today is this shifting, mesmerizing, abstract geometric shape. It looks almost like two cones touching at the tips.
It is indeed. It's a visual representation of a light cone.
Okay.
And I chose it because it really perfectly represents our core philosophy for this deep dive. Knowledge is most valuable when we are willing to question our most basic assumptions.
I love that.
Because there is absolutely nothing more basic to your daily life, to your minute-by-minute experience, than light. You, our listener, are using it right now just to process the space around you. Yet, as we are about to discover, the physical reality of light is utterly alien to human intuition.
It really is.
If we really want to understand the fabric of the universe, we have to start by understanding the medium that allows us to see it in the first place.
Okay, let's unpack this. Because the very first concept the author throws at us just completely shatters how we experience reality. We are used to time passing. You and I feel the seconds ticking by. But according to the physics laid out in this book, light does not experience time.
No.
At all. Zero. How is that even possible?
It is a massive paradigm shift, isn't it?
Yeah.
It all comes down to a concept in physics called proper time.
Proper time.
Right. The easiest way to think about proper time is to imagine it as the time experienced by the object itself. It's the time that would physically tick by on a pocket watch if you were carrying it with you on your journey.
Okay. Makes sense.
For massive objects, and by massive I mean anything in the universe that has mass, like humans or planets, or even just a microscopic speck of dust. Proper time always accrues. You can't ever stop it.
You're always moving forward.
Always. Now, if you move at incredibly high speeds, time might slow down for you relative to someone standing still on Earth. But your pocket watch is still ticking. Time still passes. But a photon has absolutely no mass.
Right.
And because it has no mass, it doesn't just travel fast. It travels at exactly the speed limit of the universe, the speed of light, which we designate as c.
Right. And at that exact speed limit, the rules they break down.
Exactly. At exactly the speed of light, the time dilation factor becomes infinite. So the proper time for a photon, the ticking of its internal pocket watch, is precisely zero.
Wow.
It does not age. It does not wait. From the moment it is created to the moment it is destroyed, not a single fraction of a millisecond passes from its own perspective.
So what you're saying is a photon really doesn't need a skincare routine. It literally never ages.
Precisely. It's forever young in the most literal physical sense of the word.
There is an example from the text that just stopped me in my tracks when I read it. So imagine a photon that is emitted from a hyperactive galaxy, a quasar, way out at the edge of the observable universe.
Right, a very long way away.
Right. It's emitted 12 billion years ago. It travels across the expanding void of space. It flies past forming galaxies. It dodges dying stars. And it finally hits a telescope lens here on Earth tonight. To us, sitting here in the present, 12 billion years have passed. But from the photon's perspective, wait, so it literally doesn't experience the journey at all.
Not at all. From the photon's perspective, it was emitted by that ancient quasar and absorbed by the glass of our telescope in the exact same eternal instant.
That is just...
To that photon, the quasar, 12 billion light years away, and the telescope sitting in a desert on Earth are the exact same point in space-time.
It's almost impossible to picture.
It is a profound realization. In relativity, we talk about the space-time interval between two events. For you and me, space and time feel like two completely different things. You move through space, and time just happens to you.
Right. I walk to the store, it takes 10 minutes.
Exactly. But for events that are connected by a beam of light, that space-time interval is exactly zero. Light isn't just a physical thing moving very quickly through the universe. It actually is the boundary of causality itself.
Causality.
Yeah, that's what the light cone behind me represents. The outer edges of that cone are the absolute limits of how one event can ever influence another event in the universe, and light is that edge.
The author uses a really great analogy to help humanize this timelessness, which I appreciated because my brain was definitely starting to hurt at this point.
It's a tricky concept.
Yeah. So imagine you're watching a movie. Normally, you watch it frame by frame in sequence. The projector shows one image, then the next, so there is a clear before and an after in the story.
Right.
Now imagine taking every single frame of that 2-hour movie and projecting them all onto the exact same wall at the exact same time. It would just be this incomprehensible, overlapping blur of light. But for a photon, that's existence. There is no sequence of events, there is no before or after, it just is.
It's a really beautiful way to visualize it. And that timelessness makes the birth of a photon all the more fascinating. Because how does something that exists outside of our concept of time actually come into being?
How's it born?
Right. The most common way, the way most of the light in your room is being made right now, is through the transition of electrons. Imagine an atom as a miniature solar system, with electrons orbiting a nucleus. Sometimes an electron drops from a higher energy orbit down to a lower one.
Dropping states.
Exactly. And the universe is incredibly strict about the conservation of energy, so that extra energy has to go somewhere. It is immediately emitted as a tiny packet, a quantum of action, determined by Planck's constant, a photon.
But the text also talks about light being born from absolute destruction, right?
Yes, and it's quite poetic. When matter and antimatter meet, say, an electron and its exact mirror image, a positron, they annihilate each other completely.
It's totally gone.
Gone. The material substance, the actual mass of those particles, literally surrenders itself and becomes pure signal. The mass is converted entirely into energy, birthing two high-energy 511 kilo electron-volt gamma-ray photons that shoot off in opposite directions.
Okay, here's where it gets really interesting, because you just mentioned mass being converted into a photon, which has zero mass. But if light has absolutely no mass, how can it physically push things? Because the book makes a huge point about this. It points out that comet tails always point away from the sun, not because of the solar wind, but because the literal physical pressure of sunlight is pushing the dust and gas away. How does a massless thing push a physical rock?
It is incredibly counterintuitive, isn't it?
Yep.
We are all taught in basic science classes that momentum equals mass times velocity. Think of a bowling ball hitting a pin.
Heavy thing goes fast, hits hard.
Exactly. So if you have zero mass, you should theoretically have zero momentum. You shouldn't be able to push anything. But that classical formula is really just an approximation for slow, massive objects like baseballs and bowling balls.
Okay.
When we zoom out and look at Einstein's full equations for energy and momentum, we find that massless particles can indeed carry momentum. It is strictly proportional to their energy.
So it's the energy doing the pushing, not mass.
Exactly. The momentum of a photon is simply its energy divided by the speed of light. It's a tiny, tiny amount of push for a single photon. But when you have trillions upon trillions of photons striking a comet in space or striking a theoretically designed solar sail, they transfer that momentum. They exert a real, tangible, physical push.
Okay, so we have this timeless, massless thing that can literally push a comet through space. Why can't we just watch it moving? I mean, I can watch a baseball fly through the air. Why is a photon so elusive?
What's fascinating here is the sheer paradox of observation. To observe something in the universe generally means to receive information from it. For most things, like a planet or the chair you're sitting in, ambient light bounces off it continuously and enters your eye, so you can watch that object persist over time. But you cannot bounce light off of light. A photon has no surface. To observe a photon, your detector, whether that's a massive billion-dollar telescope sensor or just the biological eye in your head, must completely absorb it. And in this universe, absorption is destruction.
So seeing is destroying.
Quite literally. When a photon enters your eye, it strikes special, highly sensitive rhodopsin molecules in your retina. The impact of that photon causes the molecule to physically change its shape in 200 femtoseconds.
200 femtoseconds, that's unimaginably fast.
It is. And in that infinitesimal moment, the photon completely ceases to exist. It transfers its energy to trigger an electrical cascade that travels down your optic nerve and into your brain.
So your conscious experience of seeing the world, the colors, the shapes, everything around you right now is quite literally the residue of billions of photons dying.
That's exactly what it is.
That completely changes how I look at everyday objects. You know, the book gave this example of looking at a red apple. I always thought of it like a billiard ball white light from the sun hits the apple, the red light bounces off and hits my eye.
A very common misconception.
Right, but that's not what's happening at all. The apple's surface molecules are absorbing the white light, destroying those incoming photons, using that energy, and then creating brand new red photons to emit.
Yes. The object you were looking at is a secondary source.
So to our listener, everything you see around you right now is actively glowing. It's minting freshly created light just for you.
Precisely. And this bizarre interaction between light and matter leads us directly into the quantum strangeness of light. Because if you really want to understand how weird a photon is, we have to talk about the infamous double-slit experiment.
Oh, this one.
Yes, this is where light's dual nature acting as both a wave and a particle becomes undeniable.
Yes. Okay, wait, let me make sure I'm picturing this correctly because this experiment always breaks my brain. If I set up a wall with two microscopic parallel slits in it, and I put a blank canvas or detector screen behind that wall,
Right.
if I fire just one single photon at the slits, it arrives at the back screen as a single localized dot. It acts like a tiny bullet, a distinct particle.
Correct. So far, very intuitive.
But if I do this millions of times, firing one photon after another, one by one, those random dots don't just form two stripes behind the slits, they build up an interference pattern.
Yes.
A complex pattern of alternating bright and dark bands across the whole screen. But how? If I'm only firing them one at a time, how does the photon know where to go? Doesn't it have to pick one slit or the other?
You would think so. But that interference pattern proves that the single photon was somehow acting as a wave. It passed through both slits simultaneously in a state of quantum superposition.
Both at once.
Both at once. It essentially interfered with itself, like two ripples overlapping in a pond, before finally deciding to hit the screen as a single, solid particle.
That's incredibly weird, but the spooky part, the part that really unsettled me in the reading, is what happens when you try to catch it in the act.
The measurement problem.
Yeah?
Yes. The true strangeness of this experiment isn't just the wave-particle duality, it's the role of information in the universe.
Information.
Right. If you place a detector at those slits, just to measure which path the photon actually took, to catch it going through the left slit or the right slit, the complex interference pattern on the back screen completely vanishes.
Just because you look.
Just because you looked. The photons immediately go back to acting strictly like little bullets, forming two simple stripes on the wall. And it's critical to understand that this isn't because your detector physically bumped the photon or got in its way.
Right, it's not a physical block.
Not at all. You can make the detector as gentle and passive as theoretically possible. The pattern vanishes simply because the information about the photon's path now exists in the universe.
The universe essentially knows you are watching, and it completely changes its behavior. That is wild. And the book says it gets even weirder when you introduce entanglement. I have heard of quantum entanglement in sci-fi movies, but how does it actually relate to light?
Well, scientists can create two photons together at the exact same time through a process like spontaneous parametric down conversion.
Okay, big words.
Basically, they fire a laser through a special kind of crystal that splits a single high-energy photon into two identical entangled twins. They fly off in different directions. But because they are entangled, if you measure a specific property of one of those photons, like its polarization, you instantly, immediately know the exact polarization of the other twin, even if they are now light years apart.
But how does the second photon know that the first one was measured? Does a signal travel between them?
That's the mind-bending part. No signal travels between them because nothing can travel faster than light. Space simply means absolutely nothing to them. In a quantum sense, they are not two separate things separated by a vast distance.
They're the same thing.
They are described by a single shared quantum state. The physical, spatial separation between them is a feature of the universe's geometry, sure, but it is not a feature of their shared quantum reality. They were born together, and fundamentally, they have never been apart.
So, what does this all mean? We have this timeless, massless thing that acts like a wave and a particle that knows when it's being watched and ignores the very concept of space. When we zoom out from the microscopic quantum scale to the massive cosmic scale, what is light actually doing for us?
On a cosmic scale, Light becomes our ultimate historian.
Because it takes time to travel. I love this concept that telescopes are literal time machines. When you look up at the sun today, you aren't seeing the sun as it is right now. You are seeing it as it was 8 minutes ago.
Exactly.
When you look at the Andromeda Galaxy through a telescope, you are seeing it as it was 2.5 million years ago. The entire night sky isn't a snapshot of the present, it's just this incredibly layered mosaic of the past.
It is. And if we look back as far as physics allows, we see the absolute oldest light in the universe. It's called the cosmic microwave background.
The oldest baby picture of the universe.
Right. For the first 380,000 years after the Big Bang, the universe was an unimaginably hot, dense fog of plasma. It was completely opaque. Think of it like being inside a glowing, incredibly thick cloud.
Couldn't see a thing.
Photons were trapped, constantly bouncing off free-floating particles, unable to travel any real distance. But then, at an event we call recombination, the universe expanded and cooled down just enough for those particles to bind together and form the very first atoms.
And the fog lifted.
The fog lifted. The
Yeah.
universe became transparent. And in that magnificent moment, light was finally released. Those exact same photons, the ones that escaped that ancient fog, have been traveling through the vacuum of space for 13.8 billion years.
Wow.
Over that time, the expansion of the universe has stretched them out, turning them from visible light into invisible microwaves. But they are still out there. They are washing over you right now, filling the entire sky from every direction.
It's an awe-inspiring thought, but the author also points out a massive, almost unsettling blind spot in all of this. Despite showing us the very edge of the universe and the dawn of time, light only interacts with about 5% of the universe. The rest of the cosmos is completely, utterly dark to it.
It is a deeply humbling reality. When astronomers in the 20th century, notably Fritz Zwicky and Vera Rubin, started really looking at how galaxies rotate, they realized something was very wrong.
The math didn't add up.
Exactly. The galaxies were spinning far too fast for the amount of visible glowing stuffed stars and gas that they contained. Based on the light we could see, these galaxies should have just flown apart into space like a merry-go-round spinning out of control. There had to be an enormous amount of invisible mass holding them together.
Which is what we call dark matter.
Yes. Dark matter makes up about 27% of the entire universe. And then there's the even more mysterious dark energy, which is an invisible force driving the accelerated expansion of the universe. And that makes up a whopping 68%.
So most of the universe.
Vastly most of it. And neither of these phenomena interacts with electromagnetism. They do not emit photons, they do not absorb photons, and they do not reflect photons. So to light, the very thing we rely on to understand reality, 95% of the universe is utterly invisible. It's like sitting in a massive crowded auditorium, but you only have a tiny pen light that only illuminates 5% of the people in the room.
But we still know it's there. Even without seeing it, how do we study something that is fundamentally invisible to light?
If we connect this to the bigger picture, we find that in astrophysics, not seeing is actually a profound form of seeing.
How so?
We map the invisible dark matter by watching how its intense gravity bends and distorts the paths of the light we can see. It's a phenomenon called gravitational lensing.
Oh, like looking through a warped glass.
Precisely. Imagine looking through a warped piece of glass. The glass is clear, but you know it's there because the image behind it is distorted. We read the negative space of the cosmos. The light acts as a tracer, contouring over the invisible mountains and valleys of dark matter.
That is beautiful. But it also brings us to the ultimate, inevitable future of light. The author traces a timeline toward the end of the book that is almost terrifying in its sheer scale. Let's talk about the dark era.
Yes. If we project the current laws of physics forward, the timeline gets very lonely. In about 1 trillion years, star formation will completely end. The universe will run out of the gas needed to ignite new suns. Eventually, the last stars will burn out.
Just going dark.
Fast forward to a 1 with 100 zeros after it, 10 to the 100th power years from now, and even the supermassive black holes will have evaporated away into nothingness via Hawking radiation. What remains is known as the dark era.
Paint that picture for us. What does the dark era actually look like?
It is a universe where all structure, all complexity has decayed. There are no planets, no stars, no black holes. What is left is pure light. Trillions upon trillions of incredibly low-energy, massively redshifted photons stretched out over an unimaginably vast distance, traveling forever through an endless, freezing, empty void.
With nothing left to hit.
Because there is no matter left. There is nothing left to absorb them. And yet, because they experience no proper time for those final lonely photons, They will still be experiencing their eternal now. They will carry no messages to no destinations, just pure, silent motion through infinite darkness.
It is a haunting, almost sad image, but it brings us right back to the present moment, to our own minds. Because right now, the universe isn't empty. We are here. We are the matter absorbing those photons. But how does a purely physical photon hitting a physical eye actually become a subjective, internal experience?
This raises an important question, and it is perhaps the most important question in modern philosophy and neuroscience.
Mhm.
The hard problem of consciousness.
Right.
We understand the physical mechanics, the chain reaction. We know how a specific 700 nanometer wavelength of light hits the molecules in your retina, triggers an electrical signal, and maps onto the visual centers in your brain. That's all physics and biology. But how does that cold physical data processing make the leap into qualia?
Qualia, meaning the actual subjective feeling.
Exactly. The felt experience of the color red, the warmth of a sunset. Why does processing that data feel like anything at all to you? Why aren't we just biological robots processing light in the dark? We have absolutely no idea. It remains the greatest mystery in science.
The author plays with this idea as a sort of thought experiment, a heuristic device. They ask us to try taking the first-person perspective of a photon. Now, obviously, a photon doesn't have a biological brain. It doesn't have a neural architecture. But its mode of existence is so radical, having complete information of its entire origin and its ultimate destination in a single simultaneous instant, that it makes you wonder if there is a mode of being we simply cannot comprehend. Is a photon aware?
We humans assume that consciousness requires time passing, a sequence of events, memory of the past, and anticipation of the future. A photon has absolutely none of those things. But is that the absence of experience? Or is it an experience so pure, so immediate, and so eternal that our temporal, squishy human brains simply lack the architecture to even imagine it?
That completely changes how you think about the simple act of just opening your eyes in the morning. Today, we've gone on a massive journey together. We've learned that for a photon, time simply doesn't exist. We've seen how their invisible momentum pushes comet tails across the solar system, how the mere act of measuring them erases quantum patterns in the double-slit experiment, and how ancient light from the literal dawn of time is still washing over us right now.
It's an incredible biography of a particle.
It really is. And we've looked all the way forward to the desolate, dark era, where light outlives absolutely everything else in the cosmos.
It's a lot to take in. But there is one final mind-expanding concept we haven't touched on yet, pulled directly from the final pages of the text.
Oh, right.
Throughout this entire deep dive, we've talked about light as the sole massless messenger in the universe. But theoretical physics suggests that light might actually have a sibling, the graviton.
The graviton. I've heard the word, but what does it mean for us?
If gravity is quantized, meaning if gravity operates under the bizarre rules of quantum mechanics, just like electromagnetism does, then the graviton is the theoretical massless particle that carries the gravitational force. Much like a photon, a graviton would travel at the exact speed of light and it would experience zero proper time.
Okay.
But instead of carrying the electromagnetic spectrum, it carries the physical ripples of space-time itself. Imagine that for a moment. Right alongside the light we've been discussing today, there may be a second, entirely invisible language speaking across the universe. Because gravitons wouldn't be blocked by thick opaque plasma, and they wouldn't be blind to invisible dark matter. They would pass right through it all.
They'd see everything.
If we can ever fully tune our instruments to that gravitational channel, what entirely new invisible histories of the universe might we suddenly be able to see?
Wow. A completely invisible language running parallel to the light we know. That is something for you to mull over the next time you look up at the night sky. The universe is speaking, and we are only just beginning to learn its languages. To you, the listener, the next time you open your eyes and look around your room, remember, every single photon hitting your retina has crossed the universe in an instant of its own reality, just to end its existence by giving you the incredible gift of sight. Thank you for joining us on this deep dive. Keep exploring the invisible wonders around you.